Hello? You can hear me? You can hear me, okay. We're fine, I think. Should I get started? Nika can hear me. Okay, good. All right, everyone, welcome to the last computer architecture lecture of this semester. I was warned to say, add that qualifier there because I was saying it's the last lecture and then some people didn't like that. Anyways, we have 5 research paper presentations to cover today and no time to lose. I'll get started with self-managing DRAM. This is a low-cost framework for enabling autonomous and efficient DRAM maintenance operations. And this was published in Micro 2024, just like a month ago this year. Okay, so I'll start with a brief summary. The problem is implementing new in-DRAM maintenance operations, such as better RowHammer protection, implies changes in the DRAM interface and changes in other system components like the memory controller. Modifying the interface, however, is quite an involved process that typically takes multiple years. And our goal is to ease and accelerate the process of implementing new efficient in-DRAM maintenance operations. And our key idea is to propose a simple change in the DRAM interface such that the DRAM chip can reject memory accesses that target an under-maintenance region in DRAM. And this single change in the interface allows DRAM designers to implement new maintenance mechanisms without any further changes to the interface and to other system components, but the DRAM chips themselves. We implement 3 in-DRAM maintenance mechanisms in SMD to show that SMD is useful and versatile. And our evaluations show that SMD enables performance and energy efficient maintenance operations at small area cost. And all our sources and data is open sourced at the link on the bottom. This is the outline of this presentation. I'll start with some background and motivation. Let's see at a very high level what the DRAM interface looks like today. You probably already know about these. A DRAM chip communicates with the memory controller over the DDR-X interface, where the memory controller issues DRAM commands over the unidirectional command bus, and the memory controller and the DRAM chip exchange data over the data bus. Using this interface, the memory controller orchestrates all DRAM operations by sending commands to the DRAM chip, and the DRAM chip executes all DRAM commands without question. Thus, today's DRAM interface is completely controlled by one side. And one important type of DRAM operation are those that are performed by maintenance mechanisms. You already know that DRAM is subject to many error modes, such as the ones that I show you here, that necessitate maintenance mechanisms. And these mechanisms basically just maintain DRAM data integrity. One prominent example is periodic refresh, where the memory controller periodically issues refresh commands to prevent data retention failures. And as manufacturers scale storage densities, these error modes cause memory error rates to increase. And the key point I want to make here is that continued process scaling necessitates new efficient maintenance mechanisms. And these mechanisms are defined as part of the DRAM specifications, basically. And JEDEC, composed of more than 300 companies, defines the standard and produces devices that obey the standard. The DRAM standard poses a barrier to entry for new efficient mechanisms, maintenance mechanisms, because adding new or modifying the existing mechanisms require modifying the DRAM specifications and other system components, such as the memory controller, that obey these specifications. And the key reason for the barrier to entry is that the DRAM interface is rigid. It's defined in a rigid manner. It's also not easy to release a new DRAM standard or a specification, because doing so requires a multi-year effort by the JEDEC committee, one JEDEC committee. And thus, introducing new maintenance operations take a long time. And this is just one example. The recently released DDR5 standard introduces 3 new maintenance techniques. They improve bank level parallelism and performance, improve system robustness, and error tolerance. Introducing these mechanisms was only possible after an 8-year time duration between the DDR4 and the DDR5 standard. However, if we could basically release, if new maintenance mechanisms could have been more rapidly released, these improvements could have been released much earlier or at a different time. And let me finally reiterate the problem on the problem and the goal based on what I already explained so far. So I'll summarize. Introducing new maintenance operations or mechanisms take a long time, and our goal is to ease and accelerate the process of implementing new efficient in-DRAM maintenance operations. So before I explain you our solution approach, I will quickly categorize DRAM operations into two classes. That's access and maintenance. So we're well defining the things we're talking about now. Access operations serve memory requests, typically relying on information available only to the memory controller. This can be a load instructions address or the data that you're storing to the DRAM chip. Whereas maintenance operations maintain DRAM data integrity, typically using information available only to the DRAM chip. That can be some internal refresh row counter, for example, that tracks which rows must be refreshed with the next refresh command. A key observation you can make here then is that the DRAM chip has all the information it requires to maintain itself. And a DRAM chip should maintain itself due to two other reasons. The first one is you can implement maintenance mechanisms more easily and possibly faster if you didn't need to change because doing so would not require changes in the DRAM interface, right? And second, it enables DRAM manufacturers with what we call breathing room to perform architectural optimizations without exposing DRAM internal proprietary information to other parties. And our solution approach is to enable autonomous maintenance operations in DRAM chips. However, the DRAM interface definition is too rigid to accommodate autonomous in DRAM maintenance operations. In particular, the DRAM interface is designed in a way that yields all control to the processor. So we're here on the left, or like the processor or whatever is on the left side of this scale. And our goal is to make a simple one-time change to the DRAM interface and enable autonomous maintenance operations. Another way to look at this is that we aim to give breathing room to DRAM chips such that they can perform their operations autonomously. You can, by the way, interrupt me to ask any questions. Yeah. Yeah, so the question. Yeah. That's a good question. So the question is, simplified version of the question is, why does it take so long to release a new standard, right? I'll go back to my slide about that. There are many things involved, I think, in publication of a new standard. It's not just maintenance operations. I want to make that clear first. I don't exactly know which components of producing a standard take up how much time, but the fact is basically these, like publishing a new standard takes too much time, right? Like not too much, maybe depending on who you are, what's your understanding of long time is, but it takes 5 to 8 years in this example. And even if you could develop new maintenance mechanisms in maybe 2 months, you cannot release it in a widespread manner until the standard is also released that incorporates your changes. Yes. Yeah.
So I think we are dealing with the latency. The consortium of stakeholders that were like you and there's software companies, most of them are like working with each other. We need to convince pretty much everyone that it's like think about it, it's like you're making a law in a parliament to make people happy.
Yeah, Gira is basically saying there's a lot of bureaucracy also involved. So it's not just all politics. Just you cannot just propose a new thing and then implement it the next month. You have to convince 300 plus companies involved. Yes. Okay, so going back to where we left things. Oops. Here, okay. Now I can talk about self-managing DRAM itself. So in our work, again, we introduce autonomous in-DRAM maintenance operations. This means that the DRAM chip has full control over the maintenance operations it performs. This allows us to add new mechanisms inside the DRAM chip without modifying the standard and without exposing DRAM internal proprietary information. One problem that autonomous in-DRAM operations introduce is what we call access maintenance conflicts that happen when the memory controller accesses a region in memory that's undergoing maintenance. Our solution to this problem is to make a simple change in the DRAM interface that allows the DRAM chip to reject access commands. Specifically, they will be activate commands that target under maintenance regions. In summary, SMD enables autonomous in-DRAM maintenance operations with a simple change in the interface, and it divides the work nicely between the memory controller and the DRAM chip, such that you can add new maintenance mechanisms without modifying the DRAM standard. Now we will take a deeper look at SMD, starting with SMD bank organization. And to better understand SMD bank organization, we will look at a high-level depiction of a DRAM chip. Again, the audience in the room knows these basics, but maybe on YouTube we have. Basically, bear with me while I talk to you about the basics again. So a DRAM chip contains multiple banks that share a common interface. And inside the bank, there are multiple subarrays, each of which contain multiple rows. Here's what a DRAM bank with SMD looks like. We introduced the concept of lock regions, and lock regions define the granularity of maintenance operations. The lock region bit vector indicates the regions that are undergoing maintenance currently, and the lock controller orchestrates the locking and releasing of DRAM regions. So with support for SMD in a DRAM bank, we lock a region before starting maintenance operations in that region, so that an activate command that targets that region can be rejected. Let's see how exactly we lock and release regions. In summary, there are 4 key steps. First, the maintenance operations, an operation locks the region it targets. And second, the memory controller can access regions that are not locked. And third, if the memory controller accesses a locked region, it receives a negative acknowledgement, or NAC for short. And fourth, the maintenance operation at the end will release the lock. We will take a deeper look, starting with the first step. We have our lock regions on the right. Those are DRAM rows, essentially. The controller on the left, and the lock region bit vector on the bottom. So all regions here are in the not locked state currently. So the bit vector stores all zeros in the initial state. And to preserve our collective sanity, because anyways, I will refer to lock regions simply as regions to reduce the number of locks that I have to say in the next few slides. So the maintenance operation attempts to lock region 0, and the region 0 here is not locked right now. In this case, the lock controller, acquires the region, this region 0, by setting the corresponding bit in the bit vector. And the maintenance operation can now proceed in region 0. If the memory controller wants to access a different not locked region, such as region 1 here in yellow, it checks the corresponding bit in the bit vector. Because region 1 is not locked, the access can proceed. Had the memory controller tried to access region 0, it would receive a negative acknowledgement because that region is currently locked. We will discuss how the memory controller deals with negative acknowledgements later in the slide. Once the maintenance operation ends, the lock controller releases the lock by setting the corresponding bit in the bit vector to 0. Very simple. And that's how SMD locks and releases regions. Any questions? Yes.
Cases.
Maybe I'm not understanding you. Can you maybe describe an example?
So let's say you want to perform an activation
Yes.
in bank 0,
Bank 0.
some row.
Okay.
That happens to be
Mm-hmm.
memory controller cannot send another activation
Mm-hmm.
because
Let me tell you one thing. We reject only activate commands. Does that clear things up? So basically, if you're getting a rejection as the memory controller, it means the bank is pre-charged. There's no open row from your perspective as the memory controller. You send an activate and you get rejected as the memory controller. No other command besides activates are rejected, right? That means if you send an activate command, it means the bank was already pre-charged. There's no open row in the bank. Does that clear up? Yeah, okay.
in that case, the
Yeah.
controller still needs to hold the state of whether bank is currently active.
Yeah, but the memory controller already knows which row in which bank is open. Yeah, so that's a good one. The question is why the lock regions are multiple. Why do they span multiple subarrays? First, they don't have to. Yeah, it depends on your architecture. Because we have open bitline architecture where the sense amplifier has one of the bit line going sort of to one subarray and the other bit line going to the other subarray, like two terminals, right? You cannot really have one subarray under maintenance and the next subarray being accessed by the memory controller. So you want to have at least groups of like 3 subarrays. When you lock one subarray, you want the immediate neighbors of that subarray to also not be accessed in an open bitline architecture. In a different architecture, you might have as fine granularity as just one subarray for your lock regions. We also sweep the lock region, so I'll show you some performance numbers where you can see that. Cool. So now we will look at how we control an SMD chip. Again, 4 steps. All access operations, before I go into steps, the other ones, all access operations work like they would in a normal memory control, like a regular memory controller in today's DRAM interface, with the exception that activate commands may get rejected. The memory controller needs to retry these rejected commands. It can attempt to access other lock regions that are not undergoing maintenance. And the SMD chip and the memory controller together ensure that no memory request is rejected forever. We can discuss that maybe later. I don't remember if I have slides on that. But anyways, let me know if you have questions about forward progress at the end of the talk. So we will look at how SMD handles rejections, right? But I need to, well, I would normally introduce the activate command here. You already know what the activate command does. We have our DRAM rows. If you want to access this row, you send an activate command to that row. Its function is just to ready the DRAM row for access. That's the quick recap for the activate command. An activate command is typically followed by read and write commands. The memory controller obeys what we call timing parameters that impose a minimum delay between 2 commands. And for example, we would have a timing parameter between activate and read, another one here between read and write. Now, let's go back to the activate command rejections that happen when we have access maintenance conflicts. This is an example command sequence that targets region 0, leading to such a conflict. Now, what does the memory controller do? It has to retry the rejected activate command, sometime ideally in the near future, as soon as possible. The memory controller is already used to working with timing parameters, so we simply introduce a new timing parameter. This is called the retry interval, RI, which the memory controller, like after which the memory controller retries the rejected activate command. And we determine this empirically. It's 62.5 nanoseconds in most of our experiments. While the memory controller waits for retry interval to pass, it can issue an activate command to another lock region and overlap the latency of maintenance in one lock region and access in another one. This design component in SMD that enables maintenance access parallelization builds on the basic design proposed in prior work, specifically SALP, subarray level parallelism paper. I don't know if we covered it in the lecture, probably we did. And you can look at the paper for more details. Yeah, so normally I would discuss forward progress here, but I don't have many slides on that. Do you have any questions about forward progress? I can give you the bit, yes. Yeah. Yeah, that's a good one. So the question is, when you send an activate, if you're getting rejected, how long does it take for you to realize you're rejected? In the end, so we have an analysis for this in the paper. It's 5 nanoseconds. It's less than 5 nanoseconds. That's what we argue. How we argue about it is, we look at the latency of data appearing in the data bus right after you send the read command. So there's a timing parameter for that in the standard. That should be 2.5 nanoseconds, if I remember correctly. So we consider that to be a one-way delay from the deepest end of your DRAM chip to the I/O buffer side. So you multiply that by 2 because you have to make a one-way deep inside your DRAM chip and come back from there in the worst case. So this is like a sort of worst case analysis, right? The latency could be much smaller than this, 5 nanoseconds. The other components in the critical path of this latency, they're very small, and their latency is like, access latencies are like in the order of 0.00 something nanoseconds. So anything you need to add on that path is very easily accessed. So it's 5 nanoseconds. Yeah, sure. When you're thinking about the same bank, yes. But a NAC wouldn't affect the activate command going to a different bank anyways. You had another question. Yeah, that's a very good one. So the question is, for software programmers specifically, I'm going to mention that software programmers might want predictable performance, and this seems to induce unpredictability in the DRAM interface. That's correct. And that's one of the main reasons that this paper was rejected 5 times. There are 2 ways to argue about it, I think. First, I will acknowledge that that's correct, in this design at least. You can have a design for SMD, because SMD's key idea is to really enable autonomous operations inside the DRAM chip. The way we enabled that is a bit it makes the DRAM interface a bit unpredictable. But you can do what today's standards do for refresh, for example. You can say something like, you're only allowed to reject commands in this region of time. Like, let's say you have a fixed duration, 10 seconds. In that 10 seconds, 5 seconds of this is the regular DRAM interface. I'm not going to reject anything. In the remaining 5 seconds, you can send activate commands. Some of them might be rejected, but you can still parallelize things, right? And this already exists in today's interface. You cannot always predict performance because you have many other components in your system anyways. If you're designing for predictability, then that's a different issue, and SMD can be also designed predictably. But I don't think this, like right now, the way we designed it, SMD makes the predictability issues worse in today's systems. You know about caches, all the prediction stuff going on, and how do you predict all of that? No, yes, you're right. So you already send refreshes periodically. So how do you know from software that when a refresh is going to happen? There are ways to figure them out. Yeah, because they're like fixed intervals. So if you wanted to, you could figure it out. But at the hardware level, the difference is the controller knows when to do that refresh, and it can even delay those refreshes. But with SMD, the way we implement it, the memory controller doesn't know if it's going to get rejected after it sends an activate command. Actually, the main implications, I would say, going in this direction, are for scheduling techniques. In the end, we don't have a template for a state-of-the-art scheduling memory controller scheduler design. We don't have a Verilog code for, it's like obviously the companies are not going to publish that. What could happen, I think, is some brainstorming right now a bit. Let's say that the memory controller receives the requests in some buffer and then processes them and then creates a schedule of DRAM commands. There's already a created schedule for a set of commands. Now, when you reject one of the activates, you might actually destroy the schedule. And then how do you efficiently rebuild that schedule? Could be a good direction that builds on SMD. But this is a low level, I think, issue. And it depends on a lot of assumptions you make about your memory controller design. Okay, I'll continue. No questions about forward progress, that's good. Now I'll describe how we use SMD to implement efficient in-DRAM maintenance mechanisms. We describe and evaluate 3 use cases in the paper to demonstrate SMD's versatility. These are namely fixed rate refresh, deterministic RowHammer protection, and memory scrubbing. The extended version of the conference paper here at this link evaluates 2 additional maintenance mechanisms. Those are variable rate refresh and probabilistic RowHammer protection. And we discuss how SMD can be beneficial for many other applications. We also discuss all these mechanisms in the conference paper, but we don't evaluate them in the conference paper. I'll briefly talk about fixed rate refresh. And for other mechanisms, for now, I will refer you to the paper. You know why we do refresh. DRAM stores data in leaky capacitors, and we periodically restore lost charge back to DRAM by issuing refresh commands from the memory controller. This method of performing refresh has 2 drawbacks. First, you issue commands to perform this operation, which induces energy overheads and creates contention in the memory bus. And during refresh, an entire chip or a bank is inaccessible. SMD gets rid of the first drawback by autonomously performing refresh inside the DRAM chip. And the second one by, to some extent, allowing access to lock regions that are undergoing maintenance. This is how the state machine for SMD fixed rate refresh, describing SMD fixed rate refresh looks like, but I won't cover this in detail. So you can look at the paper for more details on the state machine and also on these mechanisms. If you have a burning question about use cases, I can answer them now. Yes. Yeah, that's a good one. You can choose to implement memory controller based mitigation. Like SMD does not prevent you from having memory controller based mitigation techniques. I would say so, but that would be an opinion, not a, I think it's orthogonal to RowHammer protection, but it enables efficient in DRAM RowHammer mechanism, defense mechanisms. You have something to say? No. So now I will show you the results. We'll start by looking at SMD's hardware implementation and overhead. We require 1 modification in the DRAM interface. That's the addition of this. Sorry, my clicker is not working. Interesting. My keyboard is also not working. Interesting. Okay. We'll have to do with what we have. So the addition of the negative acknowledgements, what's that? Self-managing. Yeah, that's a poor implementation of SMD if there's a thing. Anyways, we described 2 options of how you can add this. The first one is to use a signal called alert N, which already exists in the DDR4 and 5 interfaces. Basically, you add additional meanings to a signal that's already in the direction of DRAM to memory controller. This comes at no additional hardware cost. The second option is to add a new pin for each rank of DRAM chips, and comes down to about 1.6% processor pin count for a modern many-channel system, server system. Again, we do this once to hopefully prevent future modifications in the DRAM interface from implementing new maintenance mechanisms. These are like this is the summary of DRAM chip modifications introduced by SMD. They're very small. And the memory controller also needs some additional storage to track regions that are undergoing maintenance, so that it won't repeatedly try to activate the same region before TRI passes, right? We use Remulator to evaluate the performance and energy efficiency of SMD using this system configuration. You can check the repo for more details. We configure SMD with 16 lock regions in a DRAM bank and 16 subarrays in each lock region, and with a retry interval of 62.5 nanoseconds. We use 62 single core and 64 core workloads from 5 major benchmark suites. And we evaluate, I think, 6 configurations. So the first one is the baseline DDR4 system, which does refresh every 32 milliseconds. We have SMD-based fixed rate refresh, SMD-based deterministic RowHammer protection. That's like SMD with graphene, if you remember from older lectures. We have memory scrubbing and SMD combined that combines all 3 mechanisms. And we also have the hypothetical no refresh configuration that doesn't do any maintenance at all. So this is the best, well, in one sense, it's the best you can have. This plot shows you the average speed up, that's performance, across all single workloads, all single core workloads, over the baseline system. So 1 is the baseline. And the higher the bar, the better the performance. We make 2 observations here. The first one is that all SMD configurations provide substantial speed ups, and SMD combined provides a comparable average speed up to no refresh that does not do any maintenance operations. For multi-core performance, this shows you the performance in the same terms for 4-core workloads. The x-axis shows 3 classes of workloads categorized according to their memory intensity, or MPKI as a measure of memory intensity. This is misses per kilo instruction. This is let me draw the full plot for you. This is the full plot, and we observe that SMD provides higher speed ups as the memory intensity of the workload mix increases. We show the average DRAM energy across all tested workloads normalized to the baseline. Here, the lower the bar, the better in this case. And the x-axis has the same mixes. We observe that all SMD configurations provide substantial energy savings. And we find that SMD combines provides more than half the energy savings of no refresh. To summarize, SMD enables performance and energy efficient maintenance mechanisms and provides comparable benefits to a hypothetical system that doesn't do any maintenance operations. We attribute these to SMD being able to overlap the latency of a maintenance operation with a useful access operation, and to reduce command bus interference and energy use, as the memory controller does not issue maintenance commands. So there's much more about SMD in the paper that I will not cover in this talk. I already mentioned these first 2. We also have this thing that I talked about. We evaluate a policy that, oh, I didn't talk about this one. We evaluate a different policy that SMD can apply. Basically, when a lock region undergoing maintenance receives an activate command, you can choose to stop maintaining that region immediately and serve the activate command as soon as possible. We evaluate that, and we show that it can improve performance, but by a small amount. We discuss a predictable SMD interface in the paper. You might be interested in that. And we have sensitivity analyses, which shows that performance improves with increasing number of lock regions. The smaller your lock regions get, you have more opportunity to parallelize commands, overlap the latency of maintenance and access. Your benefits increase with reducing refresh period because the baseline ends up spending more time refreshing things. And you provide similar benefits across 1, 2, 4, and 8 core workloads. We also evaluate SMD-based scrubbing and compare it to memory controller-based memory scrubbing. And we see that SMD induces 8 times less overhead at a very high scrubbing rate because you don't transmit any data over the DDR interface. You can do all the ECC checking, everything inside the DRAM chip. So this is the paper. I'll conclude very quickly. So we've seen that new maintenance mechanisms require changes to DRAM standards. And in SMD, with a simple single modification to the DRAM interface, we enable autonomous in-DRAM maintenance operations. In this way, you can implement new maintenance operations without changes to the DRAM interface. And we showcase 3 high performance and energy efficient use cases for SMD. And our hope is that moving forward, SMD enables practical adoption of innovative ideas in DRAM design, and it inspires better ways of partitioning work between the memory controller and the DRAM chip. An extended version is on archive. We have everything open sourced, and that's all for this paper. Do you have any other questions? Yes. That's one component, but that's the small component. The biggest performance benefit comes from the fact that you can parallelize accesses with maintenance operations. So maintenance operations, the memory controller does not issue commands, but they still have to be done and they take time inside the DRAM chip. It's just that by enabling by using subarray level parallelism, the idea of subarray level parallelism, while you're doing maintenance in one part of your bank, you can access the other part. And that helps a lot because when you have a high memory intensity workload, it turns out the workload is not just accessing the same subarray all the time. Yeah. Yeah. The question is, does the workload mixes have a RowHammer attack pattern mixed in? No, we didn't evaluate that. Why do you think? Yeah. 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 So we don't have that. Yes, you're right. In the archive version, we have results for different thresholds at least. So more aggressive and less aggressive thresholds. Yes. Sure.
I heard that there is this new mechanism.
Yeah. We didn't practice this, okay? So we've been submitting this work for, I don't know, 2 years, 3 years now almost. Yes, the DRAM standard, the new update to DDR5 introduces PRAC. We have a footnote to cover this concern specifically. It's concurrent work at best, but the fact that PRAC was implemented, I think, unfortunately, helped our chance. This is what I believe. This is not like science at this point, right? I think it helped SMD get in this conference because we responded to some reviews like, the industry already is going in this direction, even though we could have proposed, like, we could have published this 2 years ago. You didn't let us, and the industry implemented it. Now, with that, I think we got in more easily. I don't know why. If that's the case, right? Basically, my answer is it's concurrent work. And yeah, the idea of using Alert 10 is much earlier, though. It was first introduced in Panopticon 2019 in DRAMSec. There, it was clear that if you implement something like PRAC, you would need extra time to do refresh operations. And that extra time needs to come from somewhere. And the interface is defined in a rigid way, so you cannot ask for that extra time. So they proposed to modify the meaning of the Alert 10 signal to ask for more time. For RowHammer specifically. SMD makes it a bit more general. You can use it for other purposes. And it doesn't have to be an alert 10 signal that you use. You can add a new pin. Cool. What do you have other questions? No, okay. Then I'm done. I think we want to move to the next one very quickly, unless we have YouTube questions. Okay. Sure. I don't know, Mac, where are my downloads? Not at all. Hey, give me. Oh, no. Okay. Double. Thank you. Is my screen shared? Zoom? Okay. More Mac shenanigans. Everything is good, right? Hello, everyone. We will continue with the next paper presentation, BreakHammer. We also presented this paper last month in Micro. I had a brief self-introduction, but I'll just breeze through it. I'm a master's student in TOBE2, and I'm a visiting master's student in ETH Zurich. My research interests are in computer architecture and memory systems, and best way to reach me is via email. Today, I'm going to present, as I said, BreakHammer, enhancing RowHammer mitigations by carefully throttling suspect threads. Here's an executive summary of my talk. To make the screen bigger. Okay. And hide this. Okay. The problem is DRAM continues to become more vulnerable to RowHammer, and operations that prevent RowHammer, which we call RowHammer preventive actions, are time-consuming and they block access to main memory. Locked.
Might want to use these buttons.
Okay. That's fixed again. We introduce a new type of exploit where one can mount a memory performance attack by intentionally triggering RowHammer preventive actions to block access to main memory for extended periods of time. Our goal in this work is to reduce the performance overhead of RowHammer mitigation mechanisms by carefully throttling this performed RowHammer preventive actions without compromising system robustness. Our key idea is to throttle threats that frequently trigger RowHammer solutions. To this end, we propose BreakHammer, which observes triggered RowHammer preventive actions, identifies threats that trigger many of these actions, we call such threats suspect threats, and reduces the memory bandwidth usage of suspect threats. Our evaluations show that BreakHammer significantly reduces the negative effects of RowHammer mitigation mechanisms on performance, energy, and fairness. BreakHammer and all the data sets we use to evaluate BreakHammer are open source and available through this repository. Here's the outline of my talk. Similar to Ataberk, if you have any questions, you can interrupt me at any point. Here I show a typical computing system with a processor and a DRAM module connected through the DRAM channel. The DRAM module has several DRAM chips, and inside the DRAM chip, we have multiple DRAM banks. The DRAM bank contains a two-dimensional array of DRAM cells, each of which containing a single bit of information as electrical charge. DRAM cells are horizontally connected via word lines and organized as DRAM rows, and they are vertically connected via bit lines to sense amplifiers for DRAM accesses. DRAM is accessed at a row granularity, and today this access is not perfect, where it is vulnerable to read disturbance. Here I show a prime example of read disturbance called RowHammer, where repeatedly opening and closing a DRAM row induces bit flips in the nearby DRAM cells.
In RowHammer terminology, we refer to the repeatedly activated row as the aggressor row, and we refer to the nearby rows that observe bit flips as the victim rows. We also denote the minimum activations necessary to induce the bit flip as the RowHammer threshold, or NRH. RowHammer is becoming more, DRAM read disturbance is becoming a bigger problem with technology scaling, where in the last 10 years, we have seen more than two orders of magnitude decrease in the number of activations necessary to induce the first bit flip. Therefore, it is critical to effectively and efficiently prevent these bit flips. There have been many ways proposed by industry and academia to prevent RowHammer via RowHammer preventive actions. Here I show a non-exhaustive list of RowHammer preventive actions which one can take to prevent RowHammer. In our talk, we will focus on these two as the state-of-the-art RowHammer mitigation mechanisms adopt these two approaches. First is preventive refresh, where we preventively refresh the charge of victim rows before their aggressors have been activated enough times to induce a bit flip. And the second is row migration, where we move or migrate the contents of an aggressor row to a distant row away from its victims before it can induce any bit flips. I'll continue with the motivation of our work. RowHammer preventive actions are blocking and time-consuming operations where the memory controller cannot access a memory bank under a RowHammer preventive action. As such, refreshing kilobytes of data can block access to gigabytes of data. We evaluate the performance impact of blocking preventive actions by evaluating four state-of-the-art RowHammer solutions. Here, the x-axis shows the RowHammer threshold, the y-axis shows the weighted speedup normalized to a system with no RowHammer defense, and each bar identifies a different RowHammer mitigation mechanism. Among these mechanisms, the first three, namely Hydra, RFM, and Para, use preventive refresh as their RowHammer preventive action, and Oka uses row migration. From our results, we see that RowHammer mitigation mechanisms incur increasingly large performance overheads as RowHammer threshold decreases. And even worse, an attacker can intentionally trigger many of these actions to block access to main memory. Therefore, preventive actions can be exploited to reduce DRAM bandwidth availability. To reiterate our problem and goal, operations that prevent RowHammer lead to DRAM bandwidth availability issues as they can frequently block access to main memory. And our goal is to reduce the performance overhead of RowHammer mitigation mechanisms by reducing the number of performed RowHammer preventive actions without compromising system robustness. To this end, we propose a new mechanism called BreakHammer. BreakHammer's key idea is to detect and slow down the memory accesses of threats that trigger many RowHammer preventive actions. In our study, we refer to such threats as suspect threats. Here I show an overview of BreakHammer. BreakHammer divides the execution timeline into windows of equal length, which we call throttling windows. And inside each throttling window, observes the execution timeline is a series of activations from different threads and RowHammer preventive actions from RowHammer solutions. BreakHammer has three key stages. First, BreakHammer observes RowHammer preventive actions and attributes what we call RowHammer preventive score to each hardware thread. Second, BreakHammer analyzes these scores and identifies suspect threats that unfairly reduce DRAM bandwidth availability. Next, BreakHammer throttles memory bandwidth usage of these suspect threats. Let's start with the first operation of BreakHammer, observing RowHammer preventive actions. BreakHammer tracks the number of RowHammer preventive actions each thread triggers. To do so, it implements a RowHammer preventive action score counter. One cannot directly attribute a RowHammer preventive action score to a single thread because a RowHammer preventive action is generally caused by a stream of memory requests from many hardware threads. On the bottom, I show an execution timeline where multiple accesses from different threads result in a RowHammer preventive action. When a RowHammer preventive action is triggered, BreakHammer partially attributes each hardware thread a score that is proportional to the number of activations they have performed for the given action. I will demonstrate how we can pair BreakHammer with two existing solutions. First is probabilistic row activation, or PARA. I'll describe how PARA works briefly. Whenever the memory controller activates a DRAM row, PARA generates a random number and compares it with a threshold. If the generated random number exceeds the threshold, PARA performs a RowHammer preventive refresh on the activated row. When we pair BreakHammer with PARA, BreakHammer tracks the row activation count of each hardware thread between RowHammer preventive refreshes, and when we observe a RowHammer preventive refresh, attributes each thread a score proportional to the number of activations they perform. And our second mechanism that I will demonstrate is the latest industry solution to RowHammer, which we call per activation counting, or PRAC for short. I'll again talk about how PRAC works. Preg maintains an activation counter per DRAM row inside the DRAM chip. And whenever these counters reach a critical value, for example, close to the RowHammer threshold, it triggers what's called a backoff to request time from the memory controller for refreshes. Once this signal is received, the memory controller provides time by sending specialized in-DRAM refresh commands to the DRAM module. Similarly to Para, when we combine BreakHammer with Preg, BreakHammer tracks the row activations of each threads between backoffs, and once a backoff is observed, increments each thread's score proportional to the number of activations they have. I guess this conveys the key idea of how BreakHammer is combined with existing solutions. I would like to refer you to our paper for more implementations where we pair BreakHammer with 8 state-of-the-art RowHammer solutions. Second step of BreakHammer is identifying suspect threads. BreakHammer detects threads that trigger too many RowHammer preventive actions. Here on the left, I show a table of RowHammer preventive scores of threads in a system. We can visualize these as bars on the right, where each bar identifies or depicts the score of a thread in the system. BreakHammer performs 2 checks to detect an outlier. First, it has a safeguard area where it marks the threads with relatively low RowHammer preventive score as safe. And second, BreakHammer checks if any thread's score largely deviates from the average score of all threads. The third step of BreakHammer is throttling memory bandwidth usage. BreakHammer reduces memory bandwidth usage of suspect threads, but by limiting the number of cache miss buffers the threads can allocate in the last level cache. Cache miss buffers are used to track requests that miss in the last level cache and are currently served by the main memory. When the system boots, none of the threads have any allocated cache miss buffers, and if they need to, they can allocate all of the cache miss buffers in the system. As the systems and as the threads execute, they start making memory requests to main memory and start using these cache miss buffers. When BreakHammer detects a thread as suspect, it limits the number of cache miss buffers the thread can allocate. If a thread reaches their allocation quota, they are no longer allowed to make new memory requests that miss in the last level cache, and they must wait for their earlier requests in the memory, in the main memory to be resolved. BreakHammer restores the memory bandwidth usage back if a thread stays benign for the full duration of a throttling window. Here I show an example on the bottom part of the slide where our thread is identified as a suspect in the first throttling window, and we throttle its memory bandwidth. In the next throttling window, the thread stays benign and does not get detected. BreakHammer still throttles this thread for this throttling window, and at the end of the throttling window, because the thread stayed benign, the memory bandwidth usage of our thread is restored, and the thread continues execution without any memory bandwidth quotas. Now I'll continue with the evaluation of BreakHammer. Yes. Yes. You're saying benign applications can be identified as suspects, right? That is a possibility. If a thread is an outline in a given system, so there are like, let's say 16 threads. If 15 of them are basically not triggering any RowHammer preventive actions, and one thread is performing like triggering many of them, that thread will be identified as a suspect in that case. So it can happen. In our evaluation, I will discuss. In the paper, I guess I don't have results for it, but in the paper we do. But it can happen. But yeah, BreakHammer tracks at a very coarse, I think it's either per channel or processor chip. So you can go for more fine-grained tracking and have more data. Yes. Yes. So in the paper, we don't evaluate it because the emulator doesn't have, I will describe our methodology, but our evaluation doesn't basically have an operating system. It's trace-based, doesn't have an operating system going on. You can have those type of attacks, but it comes down to how you associate those operations with a thread. For example, you said coherence protocol evictions, right? If you define a way, for example, if someone is making a lot of evictions, you can say that this thread is evicting these cache lines or this thread is victimizing someone else. You can make it so that BreakHammer scores that thread. Or for example, if you're, I think you get the key idea. So if you can associate an operation with a thread, BreakHammer can also score that if you convey this information because it is in the processor chip. Okay, I'll continue with the evaluation. So we evaluate performance and energy of BreakHammer using Remulator 2.0 integrated with DRAM power. We evaluate a realistic 4-core system with a DDR5 module that has 2 ranks and 64 banks in total. As I mentioned earlier, we integrate BreakHammer with 8 state-of-the-art RowHammer mitigation mechanisms and compare BreakHammer paired versions of these mechanisms to their baseline versions. We evaluate 4-core workload mixes from Spec 2006, Spec 2017, TPC, MediaBench, and YCSP. We create 2 types of workloads. 90 mixes where we have a malicious core that is mounting a memory performance attack by triggering many RowHammer preventive actions. And 90 other mixes where all applications are benign. I'm going to under attack results in a bit more detail right now. We first investigate BreakHammer's effect on preventive action count as the RowHammer thresholds decrease. Here, the x-axis is the decreasing RowHammer threshold. Y-axis is the preventive action count of a mechanism normalized to their baseline version at the RowHammer threshold of 4K. The blue line shows the baseline system baseline mechanism with no BreakHammer, and the orange bar shows the RowHammer mitigation mechanism with BreakHammer. As an example to read this figure, for example, this point on the blue line means that as the RowHammer threshold decreases from 4K to 128, PRAC performs 34 times many backups. And when we combine PRAC with BreakHammer at this threshold, we see an 80% reduction in the number of backups performed. When we look at all of our results, we see that BreakHammer significantly reduces the number of preventive actions performed across all mitigation mechanisms. We evaluate the reduced preventive action count on memory latency. Here, x-axis is the memory latency percentile. The y-axis is the memory latency of benign applications in nanoseconds. The blue line is the system without BreakHammer, and the orange line is the system with BreakHammer. Here we also have a dashed black line that shows the system with no RowHammer defense. As another example to read this figure, this point on the blue line shows that, or means that 50% of requests are served within 200 nanoseconds when the system has PRAC. Across all of our results, we see that BreakHammer significantly reduces memory latency across all mechanisms. We evaluate reduced memory latency's impact on system performance. Here, the x-axis is the decreasing RowHammer threshold, y-axis is the weighted speedup of benign applications normalized to a system with no RowHammer defense, and each bar identifies a mechanism without or with BreakHammer. From our PRAC results, we see that BreakHammer significantly increases system performance. And when we look across all mechanisms, we make 2 key observations. First, as the RowHammer threshold decreases, RowHammer mitigation mechanisms incur increasingly large performance overheads, and combining them with BreakHammer significantly increases system performance when there is an attack. We evaluate DRAM energy as well. X-axis is the decreasing RowHammer threshold. Y-axis is the DRAM energy normalized to a baseline with no defense, and bars show systems with and without BreakHammer again. From our PRAC results, similar to our performance results, BreakHammer has significant energy improvements, and across all of our results, similar to performance again, as the thresholds decrease, all mechanisms incur more DRAM energy overhead, and BreakHammer greatly reduces the energy consumption of these mechanisms. To summarize our under attack results, BreakHammer significantly reduces the negative performance and energy overheads of existing RowHammer mitigation mechanisms when a memory performance attack is present. We attribute these gains to 2 aspects. First, BreakHammer accurately detects suspect threads, and second, BreakHammer effectively reduces the memory interference caused by suspect threads in a memory hierarchy. I'll now summarize our no-attack results, but we have more detailed results on these in the paper. Across 94 core benign workloads, even though it's not BreakHammer's goal to improve benign system performance, we observe that BreakHammer slightly improves memory access latency, system performance, and DRAM energy efficiency. We have more in our paper, more implementation details. For example, resetting BreakHammer's counters, tracking software threads, or system with DMAs, or systems without caches. We have our security analysis, where we provide an upper bound on the overhead that an attacker can cause without being detected by BreakHammer. And second, we have our security analysis against multi-threaded attackers that try to circumvent BreakHammer. We also have more performance results, for example, fairness results, sensitivity to memory intensity, comparison to prior works, and sensitivity analysis of BreakHammer's parameters. I would like to refer you to our paper for more results and implementation details. Now I'll quickly conclude my talk. We introduce a new exploit where one can mount a memory performance attack by triggering RowHammer preventive actions to block access to main memory for extended periods of time. We introduce BreakHammer, which observes the triggered RowHammer preventive actions, identifies threats that trigger many of these actions, and reduce the memory bandwidth usage of these threats. Our results show that when the system is under attack, BreakHammer significantly improves system performance and reduces DRAM energy. And when there is no attack, BreakHammer still slightly improves performance and energy. BreakHammer is fully open sourced and artifact evaluated, available through this QR code or GitHub link below. This concludes my talk. I would be able to have any questions you may have. So does Atabak continue, or are we taking a break?
Can you hear me through the microphone? Okay, yeah, cool. So the third paper, yes. Is this the correct screen? Okay. Cool. So the third paper today is sector DRAM. It is a practical, energy efficient, and high performance fine-grained DRAM architecture. This was published in ACM TACO, and I think I presented this this year in SRC TechCon, and in January we will present this in High Peak, the conference typically held in Europe. Anyways, yes. So I'll start with a summary. You already know about DRAM. So DRAM-based systems suffer from energy wasted by coarse-grained data transfer and coarse-grained DRAM row activation. This is because applications typically use a relatively smaller fraction of the data that they fetch from DRAM. And our goal is to design a new fine-grained, low-cost, and high-throughput DRAM substrate or an architecture that can mitigate the problem with coarse-grained systems. Our design has two key ideas. With small modifications to the memory controller and the DRAM chip, we enable data transfers that are smaller than a cache block's size in a variable number of what's called DRAM interface clock cycles. We will get to those later. And we enable activating small portions of a DRAM node based on the workload's memory access pattern. The integration of sector DRAM into a modern computing system provides significant energy savings and system performance improvement. Sector DRAM incurs a relatively small DRAM chip area overhead and performs within 11% of a high performance and relatively high area overhead state-of-the-art fine-grained DRAM architecture while achieving significantly smaller DRAM energy overhead. Sorry, achieving more energy saving. Makes more sense. So this is the outline. I'll skip the background on DRAM. You know these already. Maybe a DRAM mat is what we have multiple of inside the DRAM subarray. And inside the mat, you have the rows, this DRAM cells distributed onto a two-dimensional array. This is a different and more detailed view of the subarray, DRAM subarray. And we will look at this to understand how activate commands work. The global word line spans the whole subarray and controls local word line drivers. Those are the small gray rectangles that are not visible. And the local sense amplifiers are connected to a global sense amplifier. The global sense amplifiers are further connected to the I/O interface. To access a DRAM row, you send an activate command. When the DRAM chip receives the activate command, the global and local row decoders enable the word line of the target row. And it connects doing this connects the cells to the bit lines. Then the sense amplifiers senses the deviation in bit line voltage, amplifies the voltage and latches the values. So it's like we copy the data in the row to the sense amplifiers. To read out data in the sense amplifiers, the memory controller sends a read command. Then the column it selects with the read command is transferred to outside the DRAM chip over the global sense amplifiers and the I/O interface. That was inside the subarray. Now we look at data transfers at the granularity of a DRAM module. So each chip transmits or receives 1 byte of data from its interface. And typically 64 bytes of data will make up a cache block. That's the granularity of communication between the DRAM module or chips in your system and typically the processor. Now a DRAM chip transmits or receives 8 multiple bytes of the cache block in a data transfer burst. The burst length for this example transfer is 8 because each chip receives or transmits 8 bytes. Now a chip transmits a byte in each DRAM interface clock cycle, also referred to as a beat. And in the first beat, each chip transmits its corresponding byte. The next beat, the next 8 bytes, and so on until you transfer the last 8 bytes. Now, a key problem with this coarse-grained DRAM data transfer is that it wastes energy. Even if the processor wants to access only one word, for example, the second word in the cache block, the system retrieves the whole cache block of this word with the hope of exploiting spatial locality. However, the processor only ends up accessing, in this example, 8 out of the 64 words before it writes this cache line back to DRAM. On average, across many workloads, the fraction of used words are relatively low. Now, coarse-grained activation of DRAM rows also cause energy waste. The DRAM chip activates all mats with every activate command to transfer all the words of a cache block in one data transfer burst to maintain high throughput. However, activating all mats is also not necessary because the processor does not use all of the words that it receives from DRAM. And the unused words lead to activation energy waste. Investigate the potential energy savings. Fine-grained DRAM, like a hypothetical fine-grained DRAM design, could provide using 41 single-core workloads with the evaluation methodology we will describe next in the next slides. This is, well, not the next, but later on in the slides. This is the performance for fine-grained DRAM access. And energy benefits of fine-grained DRAM access on the left, and fine-grained DRAM activation on the right. We observe that fine-grained DRAM can provide substantial read-write and activation energy benefits. To better explain this, if your DRAM today consumes this much energy, that's the darker orange bar, a DRAM chip that enables transferring data at word granularity enables something like 30% energy benefits, 27 specifically, and 4% for activation. However, this is not easy to implement, this fine-grained DRAM row activation and transfer. It has 3 key challenges. We described those challenges here, and we also provide a classification of some of the prior work that have a relatively low area overhead to begin with. These works also propose fine-grained DRAM architectures. The first challenge is maintaining a high DRAM data transfer throughput, some of these architectures reduce data transfer throughput by 8 times, and that incurs prohibitive performance overheads. The second challenge is incurring, even though these have relatively low area overheads, we're trying to make it with the smallest area overhead possible, right? So even though they try to be area efficient, we find that some of the prior works that maintain high throughput incur large area overheads. The last challenge is to exploit fine-grained DRAM, both for DRAM access and DRAM activation. And basically, we observe that no prior work overcomes all 3 challenges, and our goal is to develop a new fine-grained DRAM architecture that can mitigate the energy waste while overcoming all 3 challenges. Now let's see how sector DRAM mitigates energy waste. It has 2 key design components. First, we find that modern high-performance, high-yield DRAM architectures already split DRAM rows into physically isolated small fixed-size mats. Leveraging this observation, the sector activation component enables fine-grained DRAM activation at low cost. And second, we observe that DRAM I/O circuitry already has a way of selecting the arbitrary byte to be transmitted in 1 beat of a burst. We slightly modify the byte selection criteria to enable fine-grained DRAM data transfer at low cost using a mechanism that we call variable burst length. Let's look at sectored activation in a bit more detail. This is our example subarray. For example, we want to enable the first 2 mats and not enable the last 2 mats in this picture. And to do so, we need to isolate the global word line from the local word line drivers. We do this by adding isolation transistors, which we call sector transistors, between the global word line and the local word line drivers. Next, we need a way of controlling the sector transistor, so we add a new control signal that we call the sector latch for each mat in a bank. And by doing so, we transform what we used to call a mat into now what we call a sector, each of which can be individually activated. So a sector is actually a mat, but you have the control. You have control over it so that you can activate one sector. It's just trying to distinguish between what already exists in today's DRAM chips and what sector DRAM proposes to add. Now let's look at the second component. I'll describe it over an example, but here we have 8 sectors in this example in a DRAM bank. Each sector sends 8 bits with a read command to a structure called read FIFO. And a relatively simple circuitry selects 8 bits to transmit over the chip I/O interface with each beat of the data transfer burst. The selection process is controlled by a burst counter that gets incremented every beat. To enable variable burst length data transfers, we simply replace the burst counter with an encoder that selects data sent by only the open or activated sectors. So if only the first and last sectors were activated, the encoder would select only these 2 sectors data. Now I'll briefly describe how a memory controller can take advantage of sector DRAM and exercise control over sectors. Integrating sector DRAM chips into a system does not have to require changes to today's standard interface, which is a nice feature to have. To explain our reasoning better, we have, you already know about this, but this is the pre-charge command, which is used by the memory controller to close and open DRAM row. And the pre-charge command will typically be followed by another activate command, right? We see that there are more than 10 unused bits in the pre-charge command's encoding in the JEDEC DDR4 standard. We use 8 of these unused bits to determine the sectors that the next activate command will open. So before you transmit the sector bits, before you send the activate command, actually. So far, do you have any questions? Good. That was sectored activation, but variable burst length also can be exposed to the memory controller with no additional changes. And for that, like that's detailed, so I'll just refer you to the paper for those details. So I'll now describe how a modern DRAM-based computing system can effectively leverage sector DRAM. Effectively integrating it to a system has two challenges. First, we transfer data between components of the memory hierarchy today in cache block granularity. However, we must enable sub-cache block data transfers for sector DRAM to mitigate energy waste. We use sector caches, whereby we extend each cache block with 1 bit of metadata for each word, and each of those new bits that we add indicate if its corresponding word is valid or not in the cache block. There are more to this than just sector caches, but implementing sector caches allow us to transmit data in cache block granularity in today's systems. Let me make it more clear. We don't have this in today's systems, but if you were to implement it in a system that we have today, you would have sub-cache block data transfers. Because we now retrieve a word with each memory access and not the whole cache block it belongs to, missing words in a cache block will cause performance overheads, as you need to repeat memory accesses. And our solution to this challenge is to develop two prediction techniques. The first one exploits the spatial locality in load store instructions, subsequent load store instructions in the load store queue. You will look at word addresses of instructions that follow each other, and you're trying to accumulate the words they reference in the youngest instruction. And the second one is a spatial pattern predictor that we tailor for predicting useful words in a cache block. I'll describe these next. So we call the first one load store queue look ahead. One load store instruction typically references or accesses one word in main memory. And our key idea is to collect these memory references from younger load store instructions in the load store queue and put the collected references in the oldest one. The oldest one would be the one that's probably executed the first. The outcome we expect is that when a load store instruction executes, it will retrieve all words in the cache block that will be used by other load store instructions that follow this executed one in the load store queue. Thereby, we expect to eliminate some of the additional memory requests, memory accesses from sector misses. However, LSQ look ahead suffers from two key drawbacks, which, in summary, prevent it from identifying all useful words. And we complement LSQ look ahead with sector predictor. The key idea of sector predictor is to maintain cache block signatures that describe which words are likely to be useful based on current word use characteristics in the L1 cache. Then we reuse these signatures when a cache block misses in the L1 cache to retrieve all potentially useful words from lower levels in the memory hierarchy. Now we'll see how sector DRAM performs. We use a variety of simulation frameworks to evaluate sector DRAM's performance, energy, area overheads, energy benefits, performance benefits, and area overheads. With the baseline system configuration that we show you here, and we evaluate two sector DRAM policies where always on keeps sector DRAM on all the time. And the dynamic policy dynamically turns sector DRAM on and off based on workload memory intensity. Specifically, what we implement is you look at your memory request queue occupancy. If it's higher than the threshold, you turn sector DRAM on, like on average across a large quantum. If the occupancy is high, that means you have a lot of memory requests coming. So you turn sector DRAM on. If not, you turn it off. It will become clear later why we do this. And we compare sector DRAM to three state-of-the-art fine-grained DRAM mechanisms. Namely, those are half DRAM, fine-grained activation, and partial row activation. And we have 41 1 to 16 core multi-programmed workloads from major benchmark sets. So I'll show you the power improvements by making use of fewer sectors. We investigate the activate and read power. Write power looks very similar to read power, so you can think of this as read and write. The x-axis shows you how many sectors you activate or read And here's the power consumption broken down to DRAM array and periphery power for activating and reading 8 sectors. This is the full plot. We make 2 observations here. First, reading or activating 1 sector can greatly reduce power consumption compared to reading or activating 8 of them. And we observe that activate power is dominated by periphery power, which is marginally affected by the number of sectors you activate. So you cannot reduce activate power as much as you can reduce read power. Then we'll look at the performance of our prediction techniques. We show different sector DRAM configurations here. I'll explain each of them. And the number of their last level cache misses, that's the y-axis, averaged across all single core workloads. So each bar is an average across all workloads. Basic has no prediction, it's just sector DRAM. So you retrieve a word, you call it a day. If you didn't retrieve all words in the cache block, you're gonna have to access it again and again and again. LAN stands for LSQ look ahead configurations that look ahead n entries in the load store queue. To give an example, LA16 looks ahead only 16 next loads and stores in the queue. Now you notice we have an LA2000 here. I didn't want to use the word impractical, but you don't have 2000 entry load store queues. So that's like a limit study almost. SP512 is the sector predictor with a history table size of 512 and sector DRAM with no prediction here significantly increases the last level cache misses you have by 3 times almost. We see that LSQ look ahead that looks ahead 128 entries combined with sector predictor can reduce this additional last level cache misses by a large margin. And there's room, I think there's still room for improvement, but this is what we have in the paper. The figure here shows you the normalized weighted speedup for heavily memory intensive 8-core workload mixes. The always on and the dynamic policies for these 2 policies that I described earlier. We observed that sector DRAM provides significant speedups for highly memory intensive workloads. We show the weighted speedup for heterogeneous workload mixes again, for medium and low intensity workloads. And here you should be able to understand why we have 2 policies. Always on will hurt performance for medium and low MPKI workloads. Why? Because you have additional sector misses. And the benefit of one thing I didn't tell you, which is an error in my slides actually that I should fix. The performance benefits come from the fact that you reduce activate power and you can relax some of the timing parameters, specifically or namely tfol, which is 4 activate window. This timing parameter limits the number of activate commands you can issue to a single DRAM rank. It's 25 or so nanoseconds in DDR4 standard. That means in 25 nanoseconds, you can send only 4 activate commands. Now, if your activate commands were to enable only 1 sector, that power constraint is not a constraint anymore. You're bound by another timing constraint. So this is where the performance benefits are coming from. You're not activating all 8 sectors at once. I don't have the average number. For example, you're activating 3 sectors, 2 sectors. Then you can send many activate commands in a tfol, not just 4. So you benefit from a higher rate of activate commands. Yeah, so we have like a tfol budget of 32 sectors instead of 4 rows, because we have 8 sectors in a row. Instead, we have something like 32 sectors per 25 nanoseconds. Yeah. And that doesn't help for medium and low intensity workloads. And the fact that you have additional memory accesses hurt your performance. But if you can identify these workloads, you can just turn sector DRAM off. That will also negate its energy benefits, but you won't incur performance overheads. So basically, you overcome the performance degradation in non-memory intensive workloads with dynamic policy. You're as fast as the baseline. If you remember from the previous slide, it also reduces your benefits a little. 17% becomes 14%. But there could be a better way to transition between always on and dynamic states. Okay, so that was the bulk of the presentation, I think. The rest is still important, but I can proceed faster. This is the system energy consumption across all tested workloads for different workload categories. I'll just make this observation that sector DRAM provides significant energy savings when you have core counts larger than 2, because the core count 2 and 1 is not, you don't have a high intensive enough workload there to provide tangible benefits with sector DRAM. We also compare sector DRAM to those 3 state-of-the-art techniques, fine-grained DRAM architectures. It greatly improves performance over basic fine-grained DRAM architectures because it does not reduce DRAM throughput. It outperforms partial row activation by 10% because it leverages fine-grained DRAM for both read accesses and write accesses. Partial row activation only benefits from fine-grained data transfer and activation for writes because, because they chose to do that, I guess. And sector DRAM performs within 11% of half DRAM. Now, half DRAM is a bit unique. It still reduces activate power. It can benefit from a higher rate of activate commands, as sector DRAM does, but it doesn't suffer from additional sector misses or memory accesses. In contrast, sector DRAM provides energy savings, more energy savings than all other prior work. It outperforms all 3 techniques because it enables finer-grained data transfer and activation than a half DRAM, and reduces background energy consumption by reducing workload runtimes over fine-grained DRAM and partial row activation. We estimate sector DRAM's processor and DRAM area overheads. I'll summarize these. So we find that sector DRAM's DRAM components take up 1.7% of DRAM chip's area, and the sector caches and the predictor take up 1.2% of an 8-core processor's area. We have more details in the paper. We have a micro benchmark performance evaluation study that basically where we basically show the more random access your workloads get, the more benefits you have with sector DRAM. And if you are to develop an adversarial access pattern, which is something like a strided access workload, you can really hurt performance using sector DRAM also. That you can induce up to 33% overhead. We also have sensitivity studies that show the effect of number of DRAM channels and how sector DRAM performs with prefetching enabled. The results for these are not surprising. The more channels you have, the better the baseline and sector DRAM performance. There is no surprising relationship. And with prefetching enabled, sector DRAM improves performance even more, which is, again, something you would expect. We have discussion on how you could provide finer granular sector support, and if basically discussion on compatibility with DRAM error correcting codes. For finer granularity sectors, you could do something like that. You can send 2 precharge commands, for example, back to back, if you need to transmit more than 10 bits, 10 sector bits. Or you can actually change the standard and actually support fine-grained DRAM, but that's more costly. For ECC, we discuss how sector DRAM is compatible with existing state-of-the-art DRAM ECC. There's no bad news. And those details you can find in the paper. I'll quickly conclude. We designed a fine-grained, low-cost, and high-throughput DRAM substrate to mitigate the excessive energy consumed by coarse-grained DRAM. With small modifications to the memory controller and the DRAM chip, we enable variable-sized data transfer bursts and activating smaller-sized regions in DRAM chips. And we show that an effective system integration of sector DRAM provides significant energy savings and performance improvements at low DRAM chip area cost. And this work was published in ACM Taco. We have an extended version of our journal paper on archive, and everything open sourced. Any questions about sector DRAM? That's a good question. I'm not an expert on the size, maybe hundreds, 100-ish of entries. Yeah. So we have a 128 look ahead size, yes. But even with 16, yeah, as long as you complement it with the spatial pattern predictor, then you're fine. Yeah, 39, yeah. The difference between this last two bars are very little. But you don't want to not have look ahead also. But this can hopefully be improved. Anecdotal experience, sector DRAM was very difficult to build because you have so many things to touch. You know, the processor, the DRAM chip, the interface. We didn't touch it so much, but you might have to. And in the processor, you have to touch the processor, the core itself, the caches, all the cache subsystem. It's just might require a lot of work to implement, but the benefits of enabling this sub cache block data transfers in the system is more than just enabling the sector DRAM. What I mean by that, for example, if you have sector caches, meaning you have that additional bit that tells you which words are valid, you can actually power off the unused parts in your caches. That saves a lot of static energy, and it's probably used in some systems even. Yeah. So that's we already have that implemented, but the idea of that comes with partial row activation, one of the priorifying DRAM architectures. That's a relatively low cost method. You just need sector caches. No prediction, you know. Cool. Then we can maybe take a break for how many minutes, Rakesh? Yeah, 7, 11. Yeah, so we'll be back at 3 p.m. Hopefully, you will be back also. 3 p.m. is correct, right? Okay. Okay, it's 3 p.m. Sharp. I'll continue with the fourth paper presentation. This is probably the last paper presentation I'll do this year. It's very exciting. So this is called Read-Disturbance in High Bandwidth Memory and Detailed Experimental Study on HBM2 DRAM chips. This was published in Dependable Systems and Network Conference this year in June. You know what this is. This is a typical DRAM-based computing system with a CPU and a DRAM module. We will look at a simplified depiction of the chip to understand another thing you don't know very well, which is read disturbance. Read disturbance has significant system-level implications because it breaks memory isolation. Right? And a prominent example is RowHammer. When you repeatedly activate a row, many times you can cause bit flips in neighboring DRAM rows. We call the repeatedly activated row the aggressor row, and the rows with bit flips victim rows. And a relatively new read disturbance phenomenon is row press. Row press induces bit flips by keeping the row open for a very long time instead of repeatedly activating it. And in extreme cases, you can see bit flips with only one activation. Here's a non-exhaustive list of recent work that demonstrates read disturbance bit flips in commodity DRAM chips on a timeline, not to scale. Many LPDDR4 and LPDDRX and DDRX chips, old and new, are vulnerable to read disturbance. In our work, we try to answer this question: what about high bandwidth memory DRAM? Does read disturbance exist in high bandwidth memory, and if so, how does the vulnerability look like? And therefore, our goal is to experimentally analyze how vulnerable modern high bandwidth memory chips are to RowHammer and row press. We experimentally characterized 6 HBM2 chips in 2 different FPGA boards. Here are 4 key results from 23 new observations we make. We see that the distribution, the read disturbance vulnerability varies across 3D stacked channels in an HBM2 chip and across DRAM rows in each channel. On average, across all tested DRAM rows, we have this interesting observation that you may induce 10 bit flips with an activation count fewer than twice the activation count needed to induce the first one. This is a bit difficult. I'll take my time to explain it here. I don't want to leave you too confused. If X hammers are enough to induce the first bit flip in a row, with 2 X hammers, you can get 10 bit flips in that row on average. We show that row press is widespread across the tested HBM2 chips, and we completely uncover the inner workings of an undisclosed on-DRAM die RowHammer mitigation technique in one tested HBM2 chip. While our observations can inspire in 8 future work, that's our hope, they can be used to craft more effective attacks and hopefully more efficient defense mechanisms. And all data and the sources for this work are also open sourced. Here's the outline of this talk. We have some background on high bandwidth memory. These chips, high bandwidth memory chips, are extensively used in important system infrastructures of today. For example, several popular machine learning applications of today rely on high bandwidth memory chips and systems. A typical HBM DRAM system consists of a compute chip and multiple HBM2 DRAM chips. And all of these are integrated into a single package to form the full system. There's a different view of the same system. The FPGA and the HBM chips reside in the same package and are connected by a silicon interposer. The memory controller in the FPGA communicates with the buffer die on the HBM chip over the HBM interface. And the HBM chip contains multiple 3D stacked DRAM dies, and each die contains one or multiple channels. And there are wires called true silicon vias or vias connect the 3D stacked channels to the buffer die so that you can communicate data from the upper levels to the memory controller. We've already looked at what's inside a channel. This is like the diagram for a single DRAM chip. The only exception here is there's this concept of pseudo channels. It's unique to HBM2. Maybe they have it in HBM3 also. But it's not very important what a pseudo channel is. It's a collection of multiple banks is a good abstraction though. And each bank has multiple subarrays, and each subarray you have many rows. And DRAM cells in a row. Now let's take a look at a DRAM cell, its leakage, and read disturbance in more detail. So each cell encodes data in fundamentally leaky capacitors. Again, something we covered earlier on. This is a simplified diagram of a cell where the capacitor stores data as charge, and access transistor enables, well, gates access to the data. And there are a number of leakage paths by which charge can exit the cell. And the important thing to note is that the stored data may become corrupted if too much charge leaks. We have a simplified diagram of the capacitor voltage on the y-axis. We see that the voltage decreases over time in an exponential decay. There's a threshold Vmin, the dashed line, under which we can no longer guarantee that the cell retains data correctly. As long as the cell is above, like cell's voltage is above this line, it's a success. However, if it drops below this Vmin, we consider it a retention failure. This is a conceptual description of retention failures, and I will transition to RowHammer, right? So these are things you know, but I just want to cover them for the YouTube audience. In order to prevent such failures, we issue periodic refresh operations to restore the charge in the cell. And there is an interval between refresh commands, which we refer to as the refresh window, and that they determine the duration between two subsequent refresh commands. Now let's take a look at the same diagram in the context of a RowHammer attack. If we issue enough activations to a nearby row, the hypothesis here is that we can accelerate the charge leakage rate to a point of failure, right? Even though this cell would have normally retained its data, by disturbing a neighboring row, we've basically we prevented it from doing so. So if we refresh the cell at this point, the refresh operation sees the corrupted data and restores the corrupted state back to the cell. So I'll now introduce the testing methodology we used in our characterization. We use DRAM bender. It used to be a DDR3 and 4 testing infrastructure. Now with this work, we adapted it to work with HBM2 chips as well. It's also open source at the same link. This is one larger photo of one of the testing setups. The unique thing about this setup is we have some heating pad on top of a heat sink, which we use to stabilize the temperature of the setup. We have a cooling fan that we use to kind of cool the thing down a bit, but it's a very, very ad hoc setup, as you can see. Anyways, we have the Arduino temperature controller that controls both the heating pad and the cooling fan to stabilize the temperature at a given point. This setup gives us fine-grained control over DRAM commands, and we can issue commands back-to-back with as low as 1.67 nanosecond latency. For methodology, I guess I will say that we carefully reuse the existing read disturbance characterization methodology as done by prior work, where we basically prevent sources of interference and use the worst case double-sided RowHammer access pattern. And the bottom figure depicts one hammer operation here. Basically opening and closing the two neighbors of a victim row here, we consider that as one hammer, so 2 activations. We measure 2 metrics in our work. First one is the bit error rate. It is the fraction of cells in a DRAM row that experience read disturbance bit flips. For this one, we activate the aggressor rows 512,000 times. That's to say we use 256,000 hammers. If this metric is higher, the RowHammer vulnerability is worse for that row. The second metric is the minimum hammer count needed to induce the first bit flip. And from now on, I'll use HC first to refer to this because otherwise it just takes too long. This is HC first, aka hammer count needed to induce the first bit flip. And as this metric becomes smaller, it means that we need a shorter time to induce the bit flip in a DRAM row. We use the data patterns depicted in this table to initialize DRAM rows prior to hammering them. I will explain how data gets laid out to DRAM rows based on an example. You have all zeros in the victim row. You fill the aggressors with all ones. I'm talking about the row stripe 0 data pattern here. And the 7 other rows neighboring each aggressor row with all zeros again. Here's what happens when you use the checkered 0 data pattern. You see how the data pattern changed. And yeah, we use these 4 data patterns. We determine also we have another data pattern. We don't have another data pattern, sorry. We determine the worst case data pattern for each tested DRAM row as the data pattern that causes the smallest HC first for that row. Note that this worst case data pattern is always one of the 4 data patterns that we test. Now we will move on to results, the interesting part. We will start with the analysis of spatial variation of read disturbance in the HBM2 chip. We have 3 key takeaways from this study. First, we see that different 3D stacked channels exhibit different read disturbance vulnerability. Second, DRAM rows near the end and in the middle of a DRAM bank experience smaller bit error rate than other rows. And third, the activation count needed to induce the first RowHammer bit flip, that's HC first. I made a mistake, I should have just said HC first. Changes with the data pattern and the physical location of the DRAM. So we'll look at the first one. You see the bit error rate on the y-axis. And we have the distribution of bit error rate across rows in each channel. So each box here shows you the distribution from one channel. We make 2 observations from this figure. First, we observe that there are bit flips in every tested channel. There's no channel that's basically resilient to RowHammer, which is expected, but it's a simple observation to make. And second, we see that bit error rate varies across channels. And I highlight here groups of 2 channels that have similar looking bit error rate profiles. And if you look at this, you can group these 2 together, these 2 together, and these 2 together, and also these 2 together. So it's like there's some sort of symmetry going on. And we'll come back to this later. This is a larger version of the same figure that covers more data patterns. I guess the data pattern affects the bit error rate distribution. You can make that observation from this. And we observe up to around 247 bit flips in a row of 8,000 bits with 256,000 hammers. This is to quantify the worst case bit error rate that we've seen in our experiment. This is a different version of the same figure that shows data from multiple chips. Here, I show this to you so that you can see that our observations are consistent across the chips that we tested. I will never show you all 6 chips. Data from all 6 chips is huge. But whatever I show you is consistent across all chips. There's no observation that we made that was specific to one DRAM chip. This is the full picture for 3 DRAM chips. I'll move on to the second one. And you can interrupt me with questions, by the way. Here we show bit error rate on the y-axis, but for each point here is a row, is a DRAM row's bit error rate. And on the x-axis, we order the rows in increasing, well, I would use the word ID or address. So as we go right, we reach the last row in the DRAM bank in this figure. And note that we're only displaying, sorry, maybe it will become more clear if I show you this. These are the subarray boundaries that we reverse engineered using RowHammer tests. And this is the last subarray in the bank. This is the last 832 rows. Just wanted to tell you that these are the last 4 subarrays in the whole bank, right? This is a small picture of the full plot. This is the full plot. From here, we observe that the bit error rate is substantially smaller in the last and the middle subarrays. than all other subarrays. We have some hypotheses for these. I'll explain them later on. You also see that bit error rate goes up and down as you move inside a subarray. The bit error rate is highest in the middle of a subarray and it's lowest at either ends of the subarray. This one I don't have a very good explanation for. This is the same figure for the 3 chips. Whatever we observe, as I said, is consistent across all tested chips. The third takeaway is about HC first. So it's a similar figure to what we've seen before, except the y-axis is HC first. You can induce a bit flip as fast as only 1.3 milliseconds with 14,000-ish hammers in the worst case. And it depends, the HC first distribution depends heavily on data patterns and also on the physical location of the DRAM chip. Again, just wanted to show you the different patterns and how the distributions look like across chips. Okay, we can move on to the second analysis if you don't have any questions. Cool. But I have time. This is sort of a new analysis we did in this paper. No prior work, as far as I know, did a similar analysis. It's a bit interesting what results we have. We look at the hammer count needed to induce up to 10 bit flips. You remember HC first, this is like HC10, HC 10th. Basically, we derive 9 other metrics based on the hammer count needed to induce the first bit flip, HC second, HC third, and so on. We make 2 key takeaways from this analysis. First, we find that on average, fewer than 2 times the HC first hammers is needed to induce up to 10 bit flips in the same DRAM row. That's what I tried to explain in the executive summary. And second, in general, if it takes many hammers to induce a bit in this to first bit flip, it likely takes fewer additional hammers to induce more bit flips in the same row. Hopefully, these will become more clear with data. So here we show you the hammer counts needed to induce up to 10 bit flips, normalized to the hammer count needed to induce the first one. We show 4 boxes for each one for each tested data pattern. And this is these are the boxes that show you the values for the hammer count needed to induce 2-bit flips in terms of HC first. On average, we need approximately 1.2 times HC first hammers to induce 2-bit flips. And here's the whole complete plot. We observe that the hammer count needed to induce up to 10-bit flips varies across rows. That's the one of the boxes, like the whiskers of the box show you the degree of that variation. Right, so you have a row where you can induce 10-bit flips with only as few as 1.2x-ish HC first hammers. But you also have other rows where it takes you 5 times HC first hammers to induce 10-bit flips. And on average, fewer than 2x. That's the green line. Hammers are enough to induce 10-bit flips. Now the second takeaway. Yeah. Yeah, that's a good point. I think this helps with, first, it's data, that like the fact that we do the analysis, like the analysis itself has some value in these sort of, I guess, projects. But other than that, you're also interested in this sort of an analysis because there's error correcting codes that can correct the first few bit flips, right? So it helps you quantify how many more hammers you would need with a type of ECC. Although better analysis would be to look at code word, look at this in code word granularity. This is row granularity. Within a code word, how many more hammers do you need to induce? The next one would be good to look at to complement like the, or maybe sort of complete the circle. I don't know, like when you include system level implications, right? Cool. So here we're gonna look at the same data, but in a different way. The x-axis shows you the hammer count. The x-axis is HC first. The y-axis is HC 10th. Well, not HC 10th, sorry. It's the additional hammer count over HC first that you need to induce the 10th bit flip. This will be more clear. Here, each point in this plot will be a DRAM row. This point represents a row that exhibits a bit flip after 30,000-ish hammers and 9 more bit flips after 80,000 additional hammers. This is clear, right? Now, this is the complete plot. We look at how x and y axes correlate, and we find that increasing HT first, I will use the word somehow, unfortunately, because I'm not allowed to use significant or anything else. It's somehow correlated with decreasing additional hammer count to induce the 10th bit flip. This shows that if a row can endure many hammers before it exhibits the first bit flip, we can likely induce more bit flips with fewer additional hammers in that row, which could be a useful observation for attackers. But we don't close that gap, right? So we don't move from this to some useful system level implication. And we see similar distributions across all tested chips. Lastly, we will look at how read-disturbance changes with the amount of time the row remains open, or this is the row press analysis, basically. I described earlier, if we activate an aggressor row many times, we can accelerate the charge leakage to a point of failure. In contrast, row press, instead of a high activation count, increases the time a row stays open. So doing so disturbs adjacent rows enough to cause bit flips without having a very high activation count. There are two takeaways from this analysis. We see that the bit error rate increases with aggressor row on time at 150,000 fixed hammer count. And second, as we keep the aggressor row open longer, DRAM rows experience bit flips at smaller activation counts. Now I'll skip these or maybe go through them very fast because this is nothing surprising compared to what row press already shows. But we have seen, basically, we have quantified the degree of row press vulnerability in HBM2 chips. That's the value of this analysis. So here, as you go right, you have a longer time, you're keeping the rows open. It's obvious or unexpected that your bit error rate will increase at the same hammer count. And that's what this figure shows. And this is at even higher activation, aggressor row 1 times, it's TRFI. You keep a row open for 3.9 microseconds and 9 TRFI. The significance of these values have to do with how long you're allowed to keep a row open according to the standard. You cannot keep it open for longer than 9 TRFI. Bit error rate, we see that it reaches at around 50% at an extreme combination of this long activation time and high hammer count. Now, this wouldn't fit in a refresh window, but it's interesting to see that you can flip almost all of the bits with row press and RowHammer. Okay, yeah, our observations are consistent again across all chips. Yes. Oh yeah, that's a good point. So the question is like, these could be, some of them could be retention errors. We look at that, we filter them out. So we do retention time testing first. We eliminate all bit flip locations where retention errors could come from, and these are not them. Because this is not a very long time also. And in the end, yeah, it exceeds 64 milliseconds, but it's not like huge. Yeah. The second takeaway is another expected observation, I would say. As you increase row on time, your the hammer count you need to induce the first bit flip reduces. Yeah, and we also see that with one hammer, in our case, that's 2 activations, you can, many DRAM rows experiences bit flips if you keep the row open for long enough. Again, exceeding refresh window. Yeah. Mm-hmm. Yeah, so that's a good question. The way we account for VRT, at least, we test multiple times. It's not like we cannot test forever, right? But it's not just we do one retention test and we call them, okay, these fail. The proportion of, or the fraction of rows, cells that fail because of retention time compared to redisturbance errors is very, very low in our experiments. It's like 0.01-ish%. So even if we didn't catch all the VRT errors, okay. So some hypotheses, and then I'll need to accelerate. So we attribute the similarity in bit error rate across groups of two channels, or within groups of two channels, to their physical placement inside the die, the DRAM die. I think, or we think, not just me, we think that groups of two channels might be sharing the same DRAM die, basically. You might have 4 DRAM dies stacked and 2 channels on each die. And maybe the process variation affects the dies in a way that they end up having similar bit error rates from RowHammer. Yes. No, it's mounted on the, well, they share the same package. So it's like one package, FPGA and HBM on the same package. So yeah, you pay 5,000 Swiss francs only to be able to test one HBM chip. Yeah. Okay. And as for the bit error rate, changing across rows in a subarray, one explanation we have, well, this is not an explanation, it's just seems to be affected by the distance of that row to the sense amplifiers. That's one hypothesis. Maybe the further away you get from the sense amplifiers, for some reason, your bit error rate tends to increase. These two things, like the bit error rate being very low in 2 subarrays, we attribute it to, well, we have 3 different hypotheses in the paper for that, but the most likely one, I think, is these subarrays are at the end of the bank, so you cannot actually replicate the data pattern in the same way in these subarrays as you would in other subarrays. The subarrays at either end have bit lines coming only from one direction. Well, also from the other direction, because you have to add the dummy sense amplifiers, but you cannot really program, well, you cannot really operate those bit lines, even if you did. So a better explanation to this would require more analysis, or maybe a physical analysis of an HBM chip, but that's not possible. So it's the best we got. Yeah. These are memory controller visible row IDs. But this is an average of like bit error rate from 32 row. Like each point here is like an average. So those sort of noise would be eliminated then. Yeah. Cool. I have one more thing normally to talk about, but I'll try to find a few things to say and move on. As another component of this paper, we also look at the on-die mitigation techniques. Maybe I'll show you this slide very quickly. In the standard, you can see that there's a target row refresh mode. I'm not talking about this one. We're trying to find other on-DRAM die mitigation mechanisms that are memory controller transparent, because this is not memory controller transparent, and we don't enable this. We have disabled TRR mode, and we're looking for the existence of DRAM die, on-DRAM die mitigation techniques that take action when you send a refresh command. And we found some. So we repeated the experiments from UTRR uncovering target row refresh in this HBM chip, and we found that every 17 periodic refresh operations, even though you've disabled TRR mode, there's a mitigation mechanism that takes action and refreshes one potential aggressor row. And it refreshes both of the adjacent rows of the aggressor row. So probably it's not Samsung. I don't know. Samsung, not Hynix, maybe. We don't know. It identifies the first row that gets activated after a TRR refresh. So after every 17 refreshes. And the row that receives more than half of all the activations between two refresh commands as aggressor rows. If you have 10 activations in a window between the first one refresh to another refresh, if one row receives more than 5 activations, that's the aggressor row. But there might be other things we couldn't uncover. And we then, of course, we bypass this mitigation mechanism. But this doesn't mean your HBM2 chips are vulnerable to RowHammer when you enable TRR mode. Right? We didn't enable TRR mode. Maybe with TRR mode, really, you cannot get bit flips. No one knows. Yeah. So we have more analyses in the paper. We look at the effect of aging on bit error rate. And we look at HC first across test iterations, that's across time. So it's like we know about variable retention time. You're looking for the existence of variable read disturbance, right? We showed some evidence for it, meaning that when you sample HC first of a row, you find X. Next time you sample it again, you might find 2X. And that's what we show in this paper, very preliminarily. And then we did another work after that with this evidence, a larger scale experiment. And we have a paper upcoming that will be presented in HPCA. And I hope to get to present it to some of you at least before HPCA. So yeah, there's variation in HC first also, which might explain, I don't know, I'm looking at you then wrong, but you know the system level attacks that say, oh, there's a probability of failure. It's not really always guaranteed to fail when you do a RowHammer attack with the same number of hammers. I think this might explain those observations. We analyze the effectiveness of error correcting codes. They don't work well if you don't supplement them with RowHammer protection techniques, because you can get more than n bit flips in a code word, where n is the limits of the ECC. And we discuss more implications for attacks and mitigations and more hypotheses to explain our observations in the paper. We'll also look at bit error rate variation across rows in each channel, bank and pseudo channel, but I didn't show you that. But you can look at the paper for that. I will skip concluding the paper, and I'll show you this link, that link, and conclude. Thank you. No questions, right? Yeah. The question is, are there real system level attacks in HBM2 chips, and what are the difficulties of doing so? First, getting the hardware is quite difficult, actually. It's like very expensive. No, I mean, it's not as widespread as DDR4. You probably won't find it in a shared cloud environment so easily. That's one reason. You have them in GPUs. You have HBM3 in GPUs also. But GPUs have many, many undocumented, very hidden layers of translation between what your code, what you think your code does, and what the hardware actually ends up doing. So I'm not aware of any work that showed RowHammer or redisturbs bit flips using GPUs, for example. Not to be confused with using GPU as an accelerator sort of thing to hammer main memory in the system, right? It's talking about dedicated memory. Yeah, I think I would say they're not as widespread. So it's difficult to find a system that has HBM to begin with, and then we're talking about testing it, figuring out the access patterns that would work against it. It's difficult. In HBM3, I think
they also have the better mechanisms implemented, mitigation mechanisms, so it will be even more difficult to figure some bit flips out. Yeah, it's how, yeah.
The screen share. I guess we have around 25 minutes, and let's switch gears, and we'll conclude the semester by going to SSDs. And kind of in the similar same spirit as what we have discussed so far, we are looking at mitigation techniques for errors, and then how can we reduce the overhead of these techniques. And so this is a work called reducing solid state drive read latency by optimizing read-retry, and this work was published in ASPLOS 2021. So I'll give a brief executive summary. So read-retry is a typical error mitigation technique, and it results in a long read latency in modern SSDs. Because we need to frequently do multiple retry steps to read an erroneous page. The goal of the work is to reduce the latency of each read-retry operation. And there are two contributions of this work. The first one is pipelined read-retry operation, PR square, which concurrently performs the consecutive read-retry operations using cache read command. And then an adaptive read-retry operation, AR square, which is to reduce the read timing parameters to exploit the reliability margin provided by the strong ECC. And both these techniques come with small implementation overhead and requires no changes to NAND flash chips. Quick results. So this work reduces the SSD response time by up to 42% and 26% on average compared to a high-end SSD which performs regular read-retry operations. And compared to the state-of-the-art baseline, it performs 29% better and 17% better on average. So this is the outline of my talk. We'll quickly look at what read-retry is in modern SSDs, then the two contributions, and then we'll wrap it up with some results. So, so as you know, NAND flash memory is a very error-prone substrate, and there are various sources of errors which shift and widen the programmed VTH states. So here, what we show is basically number of programmed states in a page, and the y-axis shows the number of cells, and the x-axis shows the cell's threshold voltage. So in an MLC NAND flash memory where each cell stores 2 bits, you find 4 states, an array state which is not shown here, but you have 3 programmed states, and you use 3 read reference voltages to identify the MSB and the LSB pages. So some error sources, you have retention loss because the charge doesn't remain in the charge trap layer. So basically the charge leaks, and you see some cells, the threshold voltage changing for those cells, and there is also interference and disturbance where you see the threshold voltage increasing for some of the cells because some programming or read disturbance causes these cells to move to the right of where they are. So these are the erroneous cells when there is retention loss, let's say. So so NAND flash memory is very highly error prone, and the main reason is also as you increase the density of the flash cell, you have much smaller gaps in between 2 programmed states. So how do we correct these or how do we mitigate these problems? So we use error correction codes typically, and we also store some parity bits for the ECC decoding. And how does it work? So you get a request to the flash controller to read a page. The flash controller sends a request to the NAND flash chip, which is a NAND command. And then you get the data back to the ECC engine. And the ECC engine corrects the data, and then you get the original data back. So the number of raw bit errors that you have in the page, if it is greater than the correction capability of the ECC engine, then you basically cannot retrieve the data back. So these are uncorrectable errors. So where does read-retry come in this whole picture? So read-retry, what it does is it basically shifts the read reference voltages in small or large increments, and then tries to read the page again, so that you reduce the number of erroneous cells that you get with the original read reference voltage. So you basically adjust the read reference voltages, and then this results in decreased number of raw bit errors. So now we look at the performance overhead of read-retry. And so in a typical read, you find the TR, which is the page sensing. Then you have the DMA, because you need to transfer the data from the flash chip to the SSD controller. So then the ECC decoding also happens. So these are the three steps that typically happen in a read operation. And if you have errors in these in this page, you let's say you have 32 errors, it's still less than the correction capability of the ECC engine, which is let's say 72 in the we show in the paper. But if there are more errors, let's say when you read the page, you get 232 errors in the whole page, and this is, I think, per 1 kilobyte. So what you do is you perform read-retry with shifted read reference voltages, and the number of errors keep reducing as you reach the optimal read reference voltage. So at some point you reach a reference number of errors which is much less than the correction capability of the ECC engine. So you basically perform this whole sequence of operations, the three steps, multiple times, n times as we show here, and you basically get the data back without errors. So read-retry increases the overall read latency almost linearly with the number of retry steps. So what we did was we also looked at, did some real characterization, device characterization, and we saw how much of an overhead it is. And based on the characterization done on 160 real 3D NAND flash chips, we see that here we show there's a lot going on here. So on the y-axis, we show the number of retry steps. And on the x-axis, you basically see the retention age, which is the elapsed time since the page was last programmed. And we also show the data for 0 program erase cycles, 1000 program erase cycles, and 2K. And these boxes that you are seeing here shows the probability of the number of read-retry steps. So let's say at the start, when you have just programmed the page with 0 retention time, you get a probability of 1, which is you are not doing any read-retry. So with 0 PE cycles, what we observe is with a retention time of 6 months, you see read-retry number of retry steps being 5. And so this is with a probability of 40%. And then let's say with 22 KP cycles, you see a gradual, the trend is seen here. You can see that the number of retry steps increases as you perform more program erase cycles. And you see that with 2000 P cycles, you reach up to 25. So the more number of P cycles you perform and the longer the retention time, the number of retry steps increases. Another insight that this paper provides is that you also perform many read-retry operations, even with modest operating conditions. So when you see the first box here, so you see that you almost perform 3 read-retry steps at, let's say, a very large, high probability, even with at a retention time of 3 months. So this is an insight that this paper provides. So how does the existing read-retry mitigation techniques perform? So what they do is they try to predict the near optimal VREF values. So you can see here, this currently shows the way the typical operation happens, which is to shift the read reference voltages to basically find so we call it the valley finding algorithm, or some people call it minima finding. So so you basically want to find the region between the two states. And then some of these, the state of the art techniques, what they do is they try to predict the actual read reference voltage and avoid all these intermediate steps where you keep shifting. So how do they do it? They try to see the process similarities between different pages. So if one page undergoes the read-retry operations, they record the reference voltage and try to apply it to the other page that has a similar process, and also try to use that read reference voltage there. Some other works we also try to use machine learning techniques for this to predict the actual read reference voltage. But the bottom line is that these disturbances cause the threshold voltage changes very fast, and also there are large shifts in the threshold voltages. So it's very hard to eliminate the read-retry operation. So that's a bit of background on read-retry. It's a bit of a tongue twister for me, but anyway, so any questions so far? Or I'll, okay. Yep. Yes, there are some studies that look at these kind of similarities across different blocks. You also have some word lines which are more error prone across all these blocks. So there are some studies which look at that. Yeah. There is no pattern, but there are similarities. Yeah. Any other questions? I'll quickly move on. So I'll move to the first contribution, which is called pipeline read-retry. So the idea of this technique is to concurrently perform consecutive retry steps. So this is the way typically the retry operation happens. So you perform the first 3 steps in the read operation, then you see that there are a lot of errors. Then you start the retry operation with a different reference voltage. So you basically start after the first operation is completed. But the idea of this work is to leverage the cache read operation. So cache read operation uses the cache buffer similar to the page buffer that is there in the flash chips, and it overlaps the read of the next page with the data transfer of the previous page. So basically what we are doing here is to perform the read of the sequential read of the same page using cache read operation. So you here what you do is, while the DMA and the ECC is going on, you perform you start the next TR, which is the read operation using cache read. So what it saves is basically some latency reduction, because you are overlapping the DMA and TDMA and the TECC with TR. So this latency reduction is around 30% for each retry step from the critical path, and it also removes the TDMA and ECC from the critical path. Now, there is a so there is a problem here, which is how do we know when to stop the next retry operation? Because it keeps going on. You perform the cache read again and again till you get the number of errors less than the correction capability. but then you only know that when the ECC sequence happens or the ECC decoding happens. So by that time, you would have already started the next read. So what happens is when you have started the read at that point, you can send a reset command to the flash to stop that operation. So that's typically how we stop this cache pipeline read retry operation. So that's about PR square. Now we'll move on to adaptive read retry. So adaptive read retry is basically exploring an idea to yeah. So what it looks at is there is a large margin between the correction capability of the ECC engine and the the number of errors in the last step of the read retry operation. So you see that even if ECC capability is around 72, in the last step you get the number of errors to be 23. So in order to leverage this, what we are trying to do here is we want to explore reducing the read timing parameters for every retry step. So here we see that every read operation takes, let's say, 20 microseconds, but we are trying to reduce that read operation latency. And basically, by doing that repeatedly for the number of read retry operations, you get a latency reduction. So this is with shorter TR, as I mentioned. But this does not come for free. So what you get is if you reduce the number of reduce the read latency, there is also going to be additional errors because that's how NAND operates. So what we are seeing is that for every step you get some additional errors, and so we need to ensure that these additional errors that are caused because of the shorter TR is less than the ECC margin. So there are some necessary conditions for this adaptive read retry to work. So the first condition is that the large ECC margin in the final retry step. So because as I mentioned, if we in the final retry step, we almost get the near optimal read reference voltage, and that's what we want. And the second condition is that if we reduce the timing parameters, then we need to explore how it affects the reliability. So based on the characterization, what we have seen is that manufacturers set these read timing parameters in a very conservative manner. So they want to cover for the worst case process variations and operating conditions. So in this paper, we do a thorough experimental analysis for all these conditions, and I'll present some quick results now. So the goal is to characterize the ECC margin in the final retry step, the reliability impact of reducing the read latency, and also look at different conditions like temperature and retention time and so on. So the methodology is that we test it on real chips, 160 real chips, and also more than 10 million pages. And this is done on an FPGA flash controller, FPGA-based custom flash controller, which can test basic commands and also test mode commands like set feature and get feature. So when we look at the ECC margin in the final retry step, we see that here we show the number of errors per 1 kilobyte data. And on the x-axis, we show the retention time in months. And let's take the worst case of P cycles, 2K. And in the final step, even at retention time of 1 year, you see that there is a large margin in the ECC margin between the correction capability and the number of errors you get. So this large margin is present even when you operate under worst case conditions. And so there is a smaller ECC margin as you kind of increase the number of P cycles and longer retention time. Next, we look at the effect of reducing the timing parameters. So here we see that we again see the number of errors, maximum increase in the number of errors at 85 degrees Celsius. And on the x-axis, we show the reduction in page sensing latency. So you see that we show 0, 12.5% reduction in the TR and so on. So if you take the worst case here, so this is a T cycle 2K and retention time of 12 months, you see that even at 25% reduction of the TR, we still are under the safe reduction point of ECC engine. The correction capability, I mean. So what we are trying to see, this study shows is that even at 25% reduction, we are still okay with reducing the latency. And this also kind of depends on the operating condition. So as you slightly increase the reduction, you see that it suddenly jumps up. So some takeaways from this device characterization: the adaptive read-retry operation can easily work in the state-of-the-art NAND flash chips, and we must properly reduce the TR depending on the current operating conditions. So when we combine this adaptive read-retry and pipelined read-retry operation, so what we get is we basically implement a read timing parameter table where we store the current P cycle and the retention time and the TR values based on offline profiling. So for, let's say, 1.5 kp cycles and retention time of 60 days, you get a TR value of 70. So we use this table to reduce the read latency in the retry operations. So when your read fails, we basically go and look up this table and get the TR value from there based on the current operating conditions, and we use the set feature operation to set this read timings. So then we perform the read retry operations with this shorter TR value. So once you get the success with the ECC decoding, you basically reset the next step, and then you set the latency back to the original value using the set feature operation. So this results in no change to the flash chips, and also there is no impact on the threshold voltage, and it's easy to combine with other techniques. Okay, now before I go to the results, any questions so far? No? Okay. So I'll quickly jump to the results. I have 3 minutes. So this evaluation was done primarily with real device characterization, but also we incorporated these results into the NAND flash models of MQSIM. And it's a state-of-the-art simulator for those who don't know. So we also evaluate on 12 real-world IO workloads, 6 from MSR Cambridge traces and 6 from YCSB. All of these are block IO traces. 2 of them are write dominant and 4 are read dominant. What are the baselines? We look at an ideal SSD which has no read retry for the upper bound of the performance. And we also look at a high-end SSD which performs regular read retry operations, and a state-of-the-art implementation from Micro 2019, which predicts the V reference voltage close to the optimal values, and also reduces the number of retry steps by 70%. Now, we first show the results compared to the baseline SSD, which performs regular read retry operations. And when we do the combination of these two techniques, the PR and AR techniques, we see that there is we show the response time, SSD response time on the y-axis, and the retention time on the x-axis for different traces with different P cycles. So the lower is better here. So you see that compared to the baseline, you get almost up to 42% reduction in the SSD response time and 26% on average. And this also works on write dominant traces, which basically you would assume that for read-dominant traces, you get a performance improvement because that's where you get the ECC errors. But then even for write-dominant workloads, which cause garbage collection, we still see a good performance improvement. Now, compared to the state of the art, we see that, so here again, we show the same SSD response time on the y-axis. What you see here is that the state of the art performs much better than the combination of pipeline and adaptive read-retry operations. The reason is that in the state of the art, they do predictions, so sometimes they can end up with the correct predicted read reference voltage, and there won't be any read-retry operations, or there can be very few retry operations. But in the case of this technique, we have to do many retry operations, but we reduce the timing parameters. So here we see that the state of the art still has a large gap compared to the ideal policy where there is no read retry. So when we try to combine our contribution with the state of the art, we see that there is a performance improvement of up to 29%. And yeah, that's basically what the result for this comparison with the state of the art. So there are more results in the paper. There is an analysis of read mechanism in modern SSDs, detailed results from device characterization. We look at how the effect of reducing individual timing parameters, reducing multiple read timing parameters, and effect of operating temperature, and how to choose the best timing parameters. I think there's a typo. We also do a detailed evaluation of PR square and AR square when applied individually, and discussion on future directions to reduce SSD read latency. So in summary, retry operations cause a long read latency in modern SSDs, and there are two contributions: pipelined read retry and adaptive read retry. And we achieve up to 42% compared to a high-end SSD, and 29% compared to the baseline, state-of-the-art baseline. And we hope that this kind of an idea and the characterization results can inspire more valuable studies going forward. And that's my presentation. Thank you so much. Any questions on this technique? Okay, then, yeah, that's it for today, I guess. And yeah, we'll close the lecture now, and I wish you all a very happy holidays. Thank you.